All right. So with this video is about when you're doing photo said this word so many times. Photoelectron spectroscopy, how to read the graphs is basically what this is about. All right. And you can see the computer is gonna over here. And I remember this wonderful story from not that I didn't hear this in person, but Niels deGrasse Tyson, Dr. Tyson, he told me how like people he's an astronomer. He probably has, I don't know if he's done this, but I wouldn't put it past him in the sense that he's like a really hardworking and insightful person. He said like people sometimes think that studying the stars is this glamorous thing where you look at these beautiful images of whatever, and then he said, well, the truth of the matter is we look at graphs like this, and a star graph is kind of similar to this. It'd be flipped, inverted, where would have dips instead of peaks. Um, it would have drops in intensity rather than uh, peaks in intensity. All right. So here's what these graphs looks like, and that's what we are going to look at today, or right now. This is awesome. All right. You can look. You're going to see on this one. You're going to see the peaks are labeled, uh, and they're labeled by the element. All right. And what we're hoping to understand is what the numbers mean and so forth. All right. All right. So the x-axis is where they chart the amount of energy that you need to to cause the atom to lose an electron. It's sometimes referred to as the binding energy. Sometimes it's referred to the ionization energy, and uh, sometimes delta Q, or change in internal energy within the atom. And so you see the two different units there. That's megajoules and electron volts. Now the y-axis basically charts how much you're getting. And if you looked at the last graph, it's CPS is counts per second. Dr. Stapiello from the University of Nottingham said that these samples take about, well, a sample of theirs would take about 3 hours to do. So this is charting at various binding energies within that 3 hours, how many counts they're seeing, like how many clicks they see per second over the span of the entire scan. 3 hours is phenomenal to me. It's like, that's just so awesome that they would look at this one, and they look at a really they look, I shouldn't say, you can say look, but they're really blasting it with electrons to create an image. So they are technically looking, but it's like in a weird way. Um, so now a couple things. You're going to see that the scale is logarithmic, and sometimes there'll be breaks in it, and it's backwards. And I think it's backwards because a lot of it has to do with like the structure of the atom. Now, when you read the graph, it's a really good idea to think of the nucleus as on the origin, so to speak, because the nucleus of the atoms is what is making it hard or easy, so to speak, or to determine the difficulty of how it is to remove these electrons. And let's say we've got this fluorine atom, all right? Now remember, the location is going to tell us where, and the height's going to tell us how many, all right? And now you've got 9 electrons, all right? Now this is a little bit of an oversimplification. It actually, its electron configuration is 1s, 2s, 2, 2p5, all right? So we should have electrons of 3 different levels of energy based upon the electron configuration. And but I like visuals, so the ones that are going to be hardest to remove are going to be the ones in the center or on the first energy level, because they're closest to the nucleus. Therefore, they're the core electrons. Therefore, they're harder to move. and or harder to remove, if you would. Um, Whereas the ones that are further out, the valence electrons are going to be easier to remove. So you would expect for this, you'd expect these two to have a peak within towards the left, and the other two to have two peaks on the right. Um, and that's how these graphs are set up, and that's how you would read them. And that's it. All right. Thank you so much, and I hope you have a good day. Bye.